system of equations in 3 variables, and sometimes it can be tedious by rewriting so much at once. So another way we can do this is use the Gaussian elimination method utilizing matrices. A matrix is a regular array of numbers, such as what we see in that little box there, and we can use the following operations to transform a matrix, such as the one given, into its row equivalent matrix of the same form. So each one of these pieces here, each one of these are what we call a row, and each one of these values we have here are columns. And within each column, we have an item, a single number. This is what we call an element. A matrix is derived from the coefficients and constants from a system of a system of equations in multiple variables. The augmented matrix is when we have not only the x value, the y value, the z value, but also what it's equal to, the constant, which is where this dashed line comes from, almost acts as the equal sign. The matrix that contains only the coefficients, so the part that only contains these values here, is known as the coefficient matrix. Just like when we were solving 3 variables, we could interchange any 2 rows, we could multiply each entry in an entire row by the same non-zero constant, and we're also able to add multiples of one row to another, just in matrix form versus written out as a system of linear equations. Let's look at our first example here. It's asking us to solve the system of equations. We've got 2x minus y plus 4z is negative 3. X minus 2y minus 10z is negative 6. And 3x plus 4z is equal to 7. Let's first write the augmented matrix for the system of equations. This matrix consists of the coefficients of the x, y, and z terms, as well as the constant term. We will write a 0 in for any missing value that's not there. So when I look at 2x minus y plus 4z equals negative 3, I'll have 2, negative 1, 4, and negative 3. With x minus 2y minus 10z is negative 6, we will have 1, negative 2, negative 10, and negative 6. 3x plus 4z is 7. We'll have 3, we have 0, y's, 4, and 7. Our goal is to write this in row echelon form. Row echelon form is when we have 1s in the diagonals, and underneath those 1s are 0s, and the rest of the values are just random numbers. So again, this is what we call row echelon form. What I'm going to do is work on getting all of my zeros underneath before I move to getting my 1s, because getting my 1s I'm able to easily just divide an entire row by something, but getting the zeros could be a little bit more tricky. So I'm first going to focus on getting this value to be 0. To do that, I'm going to multiply my second row by negative 2, so that when I add it to the first row, when I add it from the first row to the second row, that second row becomes a 0. My first row will stay the same at 2, negative 1, 4, negative 3. My second row is negative 2, positive 4, positive 20, and positive 12. When I add these together, I'll have 0, 3, 24, and 9. My new matrix then is going to still be 2, negative 1, 4, negative 3, but my new middle row is 0, 3, 24, and 9. And my bottom row is 3, 0, 4, and 7. Now I'm going to focus on getting this 3 to be a 0. To do that, I'm going to multiply my top row by -3 and add that to the bottom row, which I will multiply by 2. So that one is a +6 and one is a -6. I'll now have -6 plus 3 minus 12, +9, and my bottom row is +6, still 0, +8, and 14. Adding together, we have 0, 3, -4, and 23. Our top row stays the same. Our middle row we hadn't touched. And our bottom row now becomes 0, 3, -4, and 23. So we have our first row here. We have the zeros where they need to be. I now need to go back and fix. We started with a 0 in this middle row here, but because of some operations, we now need to go back and change. So we need to go back and fix and make sure that that second column, that bottom row, has that 0. So to do that, we're going to focus on getting this piece to be a 0. I'm going to look at my middle and my last row here. But to make it a little bit easier, I see that my entire middle row can be divided by 3 and still get an even value. So I'm just going to divide this entire middle row by 3 so that we have even values that are a little easier with smaller numbers to work with. So I'll have 0, 1, 8, 3, 0, 3, -4, 23. All right, so let's look at this value here. I could multiply the top row by -3, but when I add it, this would then become a value, and we want to keep that as 0. So I'm going to use my second row, and I'm going to multiply my second row by -3 and add it to the bottom row and replace that bottom row so that the 0 goes in the place with which we're looking for. Multiplying the middle row, I'll still have 0, -3, -24, and -9. The bottom row we don't need to multiply by anything. When I add them together, we will have 0, 0, -28, and 14. So I'll have 2, -1, 4, -3, 0, 1, 8, 3, and 0, 0, -28, and 14. So now we've gotten our zeros in the bottom left-hand corner here. To get the values of 1 in my diagonal, I'm going to go ahead and divide each row by its corresponding value, such as I'm going to divide this top row by by +2. I already have that 1 here, and then divide this row by -28. 1, -1/2, 2, -3/2. We'll still have 0, 1, 8, and 3, and then we'll have 0, 0, 1, and 14 divided by -28 is half. So we know a couple things at this point. Based on these equations then, or this matrix, when I put it back into the equation form, these are still our coefficients. So I'll have x minus 1/2 y plus 2z equals -3/2. My middle row gives me 1y plus 8z equals 3. And then my bottom row is z is -1/2. Well, if I know that z is -1/2, I can substitute 0 into my middle equation and obtain what y is. So y plus 8 times negative half is 3, or y minus 4 is 3. When I add 4 to both sides, I now know that y is equal to 7. Well, now that I know what y and z are, I can substitute both of them back into my original equation, or the top equation, obtain what x is. X minus 1/2 times 7 plus 2 times negative half is negative 3/2. So x minus 7/2 minus 2/2 is negative 3/2. Notice they all have a common denominator, so I'm just leaving them that way. X minus 9/2 is negative 3/2. Adding 9/2 to both sides, I'll have negative 3/2 plus 9/2, or 6/2, which is the same as 3. So we found our x value is 3, we found our y value is 7, and our z value is negative half. So we do the same technique, just using matrices instead of equations. Kind of makes it a little bit simpler. The goal of our Gaussian elimination is to find a matrix that's called row echelon form, which we just discovered, where these A's, B's, C's, D's, E's, and F's were values. Okay, we know that it's in row echelon form if a row does not consist entirely of zeros. Then the first non-zero element in the row is a 1. This is called a leading 1. For any two successive non-zero rows, the leading 1 in the lower row is farther to the right than the leading 1 in the higher row. All of the rows consisting entirely of zeros are at the bottom of the matrix. And if a fourth property, it is also satisfied, a matrix is said to be in reduced row echelon form, with each column that contains a leading 1 has zeros everywhere else. Which of the following matrices are in row echelon form? Which, if any, are in reduced row echelon form? Let's start looking at 1A, or part A. Notice that my diagonals are all 1s, and everywhere else to the left of it are zeros. So this is in row echelon form. However, it is not in reduced row echelon form, because the negative 3, 5, and negative 4 would also need to be zeros. Part B. Part B. 0, negative 1, 2, 1, 0, 1, 5. This is not in row echelon form, because we would need to have a 1 in this corner up here. And since it's not in row echelon form, it's not even close to being questionable if it's in reduced row echelon form. Part C, I have the zeros in the right location, but this value here needs to be a 1 in order for it to be in row echelon form. So this is not in row echelon form, and since it's not in row echelon form, it cannot possibly be in reduced row echelon form. Letter D, we have the 1s in the diagonal and zeros everywhere else. So it is in row echelon form, and it is also in reduced row echelon form. Letter E, again, the diagonals and the 0 tells us that it is in row echelon form, and because there's zeros everywhere else, is also in reduced row echelon form. Notice with letter F, we have a row of zeros. This would need to be in the bottom row, so we would need to flip-flop them, but we would still be missing a 1 in the bottom right-hand corner. So this is not in row echelon form. The goal of the Gauss-Jordan elimination is to find a reduced row echelon matrix that is equivalent to a given system of equations. And by putting it in reduced row echelon form, it automatically then solves x equals a value, y equals a value, and z equals a value, and we put it back into equation form. So when I'm looking at my first problem here, I've got 2x minus y plus 4z is negative 3, x minus 2y minus 10z is negative 6, and 3x plus 4z is 7. We're going to put this into, earlier we solved this system using the Gauss elimination system to find this matrix from a previous problem. So let's continue solving this so that we end up with zeros in the remaining locations to see if we can obtain the same results. I'm going to start, notice how I worked with the last one. I worked left to right, top to bottom. So I'm going to first start with getting negative 2 to be a 0. To do that, I'm going to multiply my second row by a positive 2 and add it to the top row. When I don't need to multiply anything by the top row, so I'm going to leave it as 1, negative 2, negative 10, negative 6. And the middle row will be 0, 2, 16, and positive 6. Adding these together, I'll have 1, 0, 6, 0. That will then be our new top row. So 1, 0, 6, 0, 0, 1, 8, 3 stays the same, and 0, 0, 1, negative half. Okay. So the left column and the middle column both have the zeros where they need to be located. So I'm going to move to the right-hand column and start at the top and work my way down. So I'm going to start with 6. When I find 6 and 2 is 0, I'll then move to 8. I'm going to multiply my bottom row because I know that these are zeros for 0, 0, 1. So because those are zeros, when I add it to anything, it doesn't matter. It's not going to change the values above. So I'm going to multiply this by negative 6 and add that to my top row. When I multiply the bottom row by negative 6, we'll have 0, 0, negative 6, 3. Adding that to my top row provides us with 1, 0, 0, 3. So our new matrix will be 1, 0, 0, 3, 0, 1, 8, 3, 0, 0, 1, negative half. The last part I need is this 8 to become a 0. So again, I'm going to multiply this bottom one by negative 8 and add it to the middle row. I'll have 0, 0, negative 8, 4. And my middle row stays the same. Now we'll add them together. We'll have 0, 1, 0, 7. Now we are in reduced row echelon form since the diagonals are in 1s and the rest of the values are in 0s. From here then we can pull the coefficients and put them back into equation form. Notice that my top one is x equals 3, 1y is 7, and 1z is negative half. So it solves us for us, giving us the solution 3, 7, negative half. So by continuing where we had left off, instead of placing them into equation form, we can use matrices to continue solving to find the solution as well. Let's try one more. Here we have the system of equations. We're first going to write the augmented matrix. We have 3, negative 4, negative 1, 6, 2, negative 1, 1, negative 1, and 4, negative 7, negative 3, 13. All right, my first goal is to get the zeros where they need to be. So I'm going to start with 2. That would be my first 0 that we need, working left to right, top to bottom. I'm going to look at my top equation and multiply it by -2. And I'm going to add that to the middle equation when I multiply it by 3, so that we have a common value. Multiplying the top row by -2, I have -6, 8, 2, -12. Multiplying the middle row by 3, we have 6, -3, 3, -3. And when we add, we have 0, 5, 5, and -15. I'll still have 3, -4, -1, 6. My 0 is now where I need it, but notice that 5, 5, and -15 are all divisible by 5. So I'm going to do that right away. 5, 5, and -15, well, dividing them by 5 gives me 1, 1, -3. And then my bottom row stays the same, 4, -7, -3, 13, since we haven't touched that yet. Okay. Our next goal then is to obtain the 4 to be a 0. Again, working top to bottom, left to right. I'll need to multiply then, let's say my top row by -4, and then add that to the multiple of 3 of my bottom row. Multiplying the top row by -4, we have -12, 16, 4, -24. And by multiplying the bottom row, we'll have 12, -21, -9, 39. Adding them together, we have 0, -5, -5, and 15. Our top row stays the same. Our middle row also stays the same. And our bottom row, notice they're all divisible. We know it has to be a positive one, so I'm going to divide them all by -5. So I have 1, 1, and -3. We see something interesting happen here. If I wanted to get our next value, let's say our next value here has to be a 0. I would then want to multiply perhaps this top row by -1 and add it to the bottom row. When I do that, then I'll have 0, -1, -1, 3, and 0, 1, 1, -3. I end up with zeros all along the bottom. This tells me if this would be replaced here, I wouldn't be able to get a 1 in the bottom right-hand corner any longer because the zeros are all there. This tells me that the equations are dependent. Equations are dependent. And because 0 would equal, in this instance, if we had them here, 0 certainly does equal 0. There are infinitely many solutions. And this concludes our lesson on solving systems of equations with matrices.